Hello, my name is Sophia Helmkamp, and this summer I had the privilege of working in the research labs of Dr. Erica Belmont. I worked on a project called Hydrogen Pyrolysis, in which we are using this hydrogen pyrolysis technique in order to determine the black carbon content of biomass. Now, first, some terminology. Biomass refers to any renewable organic-based fuel feedstock. This can be anything from energy crops, such as elephant grass, to even municipal sewage waste, but in this case we are dealing mostly with wood, specifically lodgepole pine. Black carbon, or sometimes called pyrogenic carbon, is a term for carbon that is locked in aromatic compounds, that is, fixed structured compounds within the biomass that don't break down except for a long time in any way except by combustion. Wildfires produce black carbon. They have which has a local effect and a global effect on the environment. The local effect is because black carbon can't be easily recycled back into the ecosystem because of its long-lasting nature, that it can affect how the ecosystems work. And a global effect is that there's a measured 1.5 petagram yearly carbon sink around the globe, and black carbon creation by wildfires is considered to be one of the reasons that this sink occurs. The goal of our research this summer was to compare the black carbon content in various samples of lodgepole pine, specifically unburned healthy pine, and then burned, as in burned from a wildfire, healthy pine, unburned beetle kill, and burned beetle kill. So why is hydrogen pyrolysis specifically the method we use to measure the black carbon content? Well, there's a lot of different methods to measure black carbon, but none of them is universally accepted by the scientific community as the correct method to measure it. However, there's a kind of a continuum of black carbon. You have on one side slightly charred biomass, and on the other side just full-on graphite. And hydrogen pyrolysis in particular measures the widest and most representative fraction of black carbon on this continuum. So it could be considered the best way to measure a comprehensive black carbon content of any biomass sample. What is hydrogen pyrolysis? Well, pyrolysis is a technique of treating biomass where you heat it to somewhere between 600 and 900 degrees Celsius under an inert environment that is oxygen-free, therefore it doesn't combust. Instead, it does two things. It chars the biomass and it volatilizes or turns to gas a lot of the compounds in the biomass. Hydrogen pyrolysis is where the inert gas that you use for the pyrolysis is not nitrogen or argon or one of the other common inert gases, but hydrogen. Specifically, the hydrogen pyrolysis used for this black carbon content determination also has a couple other characteristics in that it's performed under high pressure, and there's a molybdenum catalyst you add to the biomass sample in order to encourage the volatilization of everything except black carbon. So the technique works because in this hydrogen pyrolysis, you start with a regular biomass sample plus this catalyst, and you end up with nothing except black carbon and then ash and the remainder of the catalyst. So the main thing I had to do with the research over the summer was to help the team design and prepare this HyPy Reactor in order to run these tests on the various kinds of lodgepole pine. The reactor consists of a quartz glass tube in which you place the biomass sample, which then rests in a piece of stainless steel pipe that's a ½ inch in diameter. You wrap that in high temperature heat tape and flush it with high pressure hydrogen gas, and then you use the heat tape to ramp the temperature of the reactor and thus of the sample with the temperature profile that you want in order to complete the hydrogen pyrolysis. We designed this reactor based on the designs of other teams have used that are recorded in scientific literature, with a few modifications to suit our needs. Particularly, a lot of those designs featured a dry ice trap downstream of the reactor, where you condense the volatiles that have pyrolyzed off of the sample in order to study them. But since we are only interested in what's left behind after the hydrogen pyrolysis, because we're using it to determine black carbon content, we didn't need the dry ice trap. We also ran into a little bit of difficulty with the molybdenum catalyst. Most of the other research groups recorded in literature used ammonium dioxidithiomolybdate. However, that is not commercially available currently, and the price to get it fabricated was exorbitant, so we substituted ammonium tetrathiomolybdate and adjusted some of the parameters so that it would have approximately the same effect. We also had some equipment limitations that led to less precision with the temperature ramping. Specifically, the heat tape, while effective in getting to the temperatures that we wanted, isn't the most precise in straight line temperature ramps followed by flat holding at given temperatures. And so we had to approximate a little bit of our temperature ramp, which I will discuss a little bit later in this presentation. Here is an illustration of the hydrogen pyrolysis reactor. You can see that at the beginning, on the right side, we have our hydrogen intake. It says hydrogen or nitrogen. That's because we ran some pre-tests with nitrogen as well as flushed the reactor with nitrogen after every test in order to avoid things like hydrogen embrittlement. And the pre-testing with nitrogen was in order to be sure that our setup worked before we used something as volatile as hydrogen in such a high pressure, untested situation. And you can see the reactor and the length of preheat line and the reactor that would be heated to 550 C. That's where the heat tape was. There is a condenser downstream of the reactor, but it's not a dry ice condenser. It's only an ice bath, and its purpose actually isn't as a condenser, but simply as a cooling mechanism so that we did not overheat our digital pressure gauge or release high temperature hydrogen into the environment, which is dangerous. We also mixed nitrogen, low pressure nitrogen, with our hydrogen outlet in order to reduce the risk of combustion of the hydrogen at the outlet. Now some initial data that we had to use in order to figure out how best to do this temperature profiling. So I mentioned that the heat tape is not the easiest to work with regarding getting the temperature profile that we wanted. The temperature profile that we wanted was a heat ramp of 50 degrees C per minute until we reached 300 degrees Celsius. 300 C is the temperature where the molybdenum catalyst all decomposes into MOS2, which is actually the catalyst that we need for the reaction. And then after that, we raised the temperature at 10 C a minute until we reached our final temperature, which was 550 C. In order to get this temperature profile using our heat tape, we ran initial tests, as I mentioned, with nitrogen, with no sample in the reactor, merely to see how the heat tape behaved and how to get this temperature profile best by adjusting the heat tape temperature and by adding and removing insulation, that sort of thing, in order to get this temperature profile. Here you can see a graph of our final temperature profile that we determined was close enough to our heating rate that we desired that we could use this then with molybdenum, with the sample, with the catalyst, in order to actually run our hydrogen pyrolysis tests. It was a combination of setting the temperature controller to a higher temperature than our actual desired final temperature and removing insulation at the 300 degree point in order to slow the heating rate. And we got it to the point that up to about 300 degrees C, we were at approximately 47 degrees C per minute as our heating rate. And after 300 degrees C, we are at an average of 13 degrees C per minute, which, as I said, we determined was close enough to our desired heating rates as to serve the purpose. So we ran a test with some healthy pine in our hydrogen pyrolysis reactor. And once we had run the test and gotten the hydrogen pyrolyzed sample out of the reactor, we then put it in an analyzer, a thermogravimetric analyzer, or TGA, which in this case pretty much had the function of burning off the burning off the black carbon and leaving only the ash behind in order for us to see how much black carbon was in the sample and how much ash was. If you look at the graph on the right, at the point on the top that says oxidation, there's a sharp drop in the solid line of remaining mass percent. Now the solid line is how the sample that had been pyrolyzed in the hydrogen pyrolysis reactor reacted in the thermogravimetric analysis. At oxidation, that is combustion, that is the burning off of the remaining black carbon, the mass of the sample dropped by approximately 20%. That tells us that that sample was about 20% black carbon, and the remaining 80% was ash and leftover catalyst, and etc. Now, this is compared with the dashed line on the graph. That dashed line represents the TGA analysis of some sample that, instead of being put through the hydrogen pyrolysis reactor, was simply pyrolyzed, standard pyrolyzed, under nitrogen conditions. I mentioned at the beginning that simply pyrolysis has two functions. It volatilizes a lot of the biomass, but it also chars a lot of it. And you can see the amount that it chars in the much sharper drop that the dashed line has at the oxidation point. That means that close to 90% of the remaining ash burned off in combustion. Compare that to the mere 20% that burned off in the combustion of the char that had gone through hydrogen pyrolysis. This means that the biomass that had been standard pyrolyzed created a whole lot more black carbon than had been originally in the sample that could burn off in the TGA and show that in the 90% mass drop, as opposed to the hydrogen pyrolysis, which merely shows us how much black carbon was in the sample initially and did not create any more, because the hydrogen pyrolysis merely volatilizes everything except black carbon in the sample and doesn't char any new black carbon. So this then is the value of the hydrogen pyrolysis as a technique to determine black carbon. If you do regular nitrogen pyrolysis, you create black carbon rather than simply isolating it, whereas in hydrogen pyrolysis, you isolate it. And finally, to show the results of the different kinds of wood that we were testing in the hydrogen pyrolysis reactor, you see on the left a sample tube loaded with sample before hydrogen pyrolysis. And then on the right, we have two examples of post-hydrogen pyrolysis sample tubes. The middle picture shows the post-hydrogen pyrolysis sample that is representative of either unburned healthy pine, burned healthy pine, or unburned beetle kill. You notice there's a very small amount of sample left in that tube. That means that most of that sample was not black carbon. Most of it volatilized away in the hydrogen pyrolysis reactor and left only a little bit of black carbon and ash behind. That means that there's very little black carbon in unburned healthy pine and unburned beetle kill, and also, interestingly enough, very little black carbon in burned healthy pine. Compare that to the amount left in the quartz tube on the very far right. That is the burned beetle kill after it has gone through hydrogen pyrolysis. There's a lot left, which means that a large fraction of the burned beetle kill was, in fact, black carbon. Much larger fraction of it is black carbon in burned beetle kill, even than in burned healthy pine. And this is the interesting result of this experiment, that beetle kill, more even than the presence of burning at all, affects the amount of black carbon. Basically, lodgepole pine that is first beetle killed and then burned has a lot more black carbon than lodgepole pine that is merely burned in a wildfire. After I concluded my summer research, the team continued and applied this hydrogen pyrolysis and continued working with the Badger Creek fire, and they came up with the results that beetle kill raised the black carbon content in this wood that had been burned by the wildfire by a factor of 18. That's an extremely significant factor. And the team hopes to continue to use the HyPy reactor to analyze the results of the recent Mullen fire. I hope and suspect I will be part of that analysis when I return to the research team over winter break in January. Thank you.